them to align in the same direction without creating difference in the relative angles, right? So the question is whether the ground state spontaneously choose any particular direction, or will ground state be randomized as we saw in the large U limit, okay? So to address this issue, what we did is we start with a seed state where all rotors are pointing in one direction. So we start from this seed state where all rotors are pointing along direction phi, okay? And then now we project out excited state by applying this operator. And in general, this ground state may depend on that angle phi of the seed state, okay? So I put that index here. And the question is, will the ground state remember the angle, information about the initial angle or not? Okay? This is just one way of telling whether there's only unique ground state or many ground state. Okay? Okay. And then we yesterday were able to represent this ground state in this path integral representation. Okay? So the picture is that you start from some initial configuration of rotor whose angle is given by this angle of the seed state, okay? And then your wave function amplitude of your ground state at angle theta gives the final boundary condition at time t. And then to compute this ground state amplitude, you sum over all paths that this rotor can have, connecting this initial angle and this final angle, okay? And each path has certain weight. Not all paths have the same weight, and each path has weight, and whose weight is determined by this action. This action is a function of path, right? So if you choose one path, this action spit out one number. And e to the minus that action is the probability amplitude coming from that path. But there are many paths, and you sum over all paths with this weight, okay? So this is the prescription. So this gives us the ground state, okay? Now our goal is whether the ground state obtained this way our goal is to see whether this ground state has any information about our seed state or not. So this is the goal. And to see that, we decided to look at the expectation value of one operator that can tell the direction of rotor. We can choose any point, okay? But let's choose, this is the origin, and we compute the expectation value of this operator defined at the origin of the space, okay? And this is the sandwich with the ground state, right? So this is the expectation value of the rotor angle of the rotor at side 0 with respect to computed with respect to that ground state, okay? If this is 0, that means there's an equal probability for this rotor to point in any direction. Then that means ground state doesn't remember the phi. If it is non-zero and depends on phi, that means somehow still ground state retains the memory of my seed state. Okay? And then mathematically, this expectation value can be written as another path integration, which we derived yesterday. And because this expectation value is made of psi star and psi, and each psi is given by this path integration for time t, you guessed the right solution is given by path integration between time 2t. So you first evolve for one ground state and evolve another ground state, and you glue them at the center, right? And then this is just one number. So the right-hand side is just a number. So the prescription is that at time minus t, you have this boundary condition coming from the phi dependence of one of the ground state in the expectation value. And at time, future time t, it also satisfies this boundary condition. And then you sum over all paths that connects these two endpoints, right? And then each path is weighted by the same action, but because we are computing this expectation value, we have one more insertion here. Okay, so this is the angle at the origin side 0 evaluated at time 0, right? Because we are now, because this, we choose the time where the ground state is glued to be the time 0 here. Okay. So this, so far, this is the exact expression, but but our main interest now is to compute this in the limit that this t is much larger than t is much larger than u, in which case 1 over g squared is very large. Okay? So when this prefactor is very large, this path integration is dominated by the path which minimizes this action. Okay? And that path that minimizes this action is the path where angle doesn't change at all across time, between time minus t and t, right? So that way you don't have any gradient in the time, and also you don't have any gradient in space, right? So that is the minimum action path, okay? And then in the limit that g is small, the fluctuation around this path will be small. So we expanded this action. So we consider the saddle point path. So saddle point path is phi at all time at all site, right? Then we consider small fluctuation. The fluctuation can in general depends on site and time, right? And then we consider this small fluctuation and then expanded this section to the quadratic order in this fluctuation. So this is an approximation that is valid only in the small coupling limit, okay? And then the last thing we did is that because in the real space and time, there's a coupling between different sites. So although it's a Gaussian, it is different sites and time, they are coupled with each other. And to be able to do this path integration is convenient to go into the basis where this action has no coupling between different modes. Okay, so we did the Fourier transformation, okay, into frequency and momentum space. And in that frequency and momentum space, indeed, the same action become diagonal. There's no coupling between modes with different momentum and different frequency. Okay? So the action is sum of term, which depends on the amplitude of certain mode. Okay, so this theta prime omega k is the amplitude of the mode whose frequency is omega and wave vector is k, right? So k equals 0 mode is the mode where every rotor fluctuates uniformly across the space. Okay, and at certain frequency in omega, right? And then this amplitude can fluctuate independently from mode by mode, so therefore you have to sum over all possible amplitude for different mode, right? And then this term here is the one that determines how much action is cost how much action cost is when you create this dose excitation. Okay. Smaller the frequency, the cost of action is smaller, because when frequency is smaller, it changes slowly with time, so therefore derivative will be smaller, right? And because there are two derivatives, we have a quadratic term in frequency that you can see, right? And also, because of this gradient term in space, the modes that are more easily excited are the ones whose wave vector is small or wavelength is large, right? So in space, if this is a real space, you can create a uniform mode or some sinusoidal mode or fast mode like this, right? But the modes with a small wave vector create a small difference in relative angle, so therefore they cost less action. That is encoded in this term, epsilon of k. So this is like how costly it is to create a mode with momentum k or wave vector k. And then this is given by this equation here. So mu is summed over all direction, 1 to d. In d is the space dimension. The details are not important. As I mentioned yesterday, important thing is that this vanishes quadratically when k goes to 0. Because when k is 0, all rotors fluctuate together without costing any action energy from here. So they are free. When you create a very long wavelength mode, energy cost is non-zero, but it's small because the neighboring spins are almost perfectly aligned. There are very little gradient. So that is encoded in this equation, which goes as a k squared in the small k limit. Okay? And then this omega and k takes some discrete value when t and system size L is finite, because you have to impose the right boundary condition. In space, this wave pattern has to come back to itself due to the periodic boundary condition. And that can happen only when you choose some particular wave vector, right? And that is this condition. So in each direction, wave vector is quantized in the unit of basically 2 pi over L. L is the linear system size.
So if the lattice is infinite, there is no need to add this vector, or this vector can assume any...
That's right. So that's where we are going. So when the system size is very large, the spacing between different modes become very, very small, right? But it's safer to start with a finite system size and then take the large.
You turn k into a continuum.
That's right. That's what happened. That's right. Yeah, good. You're on the right track. So, and then frequency also is quantized, because when t is finite, when time evolution is finite, then the allowed frequency mode that satisfy this boundary condition here is this like a sine mode and with a 2 oscillation, etc. Okay, so frequency is quantized in the integer of pi over 2t to satisfy that condition. And then, of course, overall factor 1 over g squared, because when t is large, it's harder to create such distortion. Okay, so that's right. Okay. And then finally, we are computing this for this observer, and these observers is localized at some particular time and particular site. So in Fourier transformation, it includes all frequency and momentum. But one minor detail is there's this form factor, which is either 1, 0, or minus 1. And this just denotes the fact that for certain mode, like integer frequency, integer n mode, there's a node at the origin at t equals 0. And that mode doesn't contribute to the fluctuations of this operator inserted at t equals 0. Right? That's why there's this, form factor. But this is kind of minor detail. Okay? And then, okay, so then for each frequency and each momentum mode, I have some expression to integrate. Now it's a finite dimensional integration, just one complex variable integration for each omega and each k, right? And this integration is something we can do exactly, called Gaussian integration. How many of you have done the homework? The Gaussian integration. Okay, some of you, okay. So if you have not done it yet, I strongly encourage you to do it. Okay. And if you do the Gaussian integration here, then you arrive at this expression. Okay, so we are not going to derive this, but it is straightforward. And it's in the lecture note, and it's homework 3. So I encourage you to do it. Okay, but we are going to spend some time, finally, to extract some interesting physics out of this formula. Okay, that's what we are going to do today. So maybe any more question about the derivation of this formula? Okay, at least even if you didn't understand, you see where it comes from, I guess. Okay, so let's see what this formula tells us. Okay, so first of all, the expectation value depends on the phi because the saddle point is centered at phi. Okay, but then this rotor at the origin will fluctuate around phi, right? And then if you average over something that fluctuates around some particular angle, then the magnitude of that average in general will go down, right? How much it goes down is encoded in this expression here. This is something that is less than 1 because it's e to this something negative, okay? And different frequency and momentum modes contribute to the suppression of the angular momentum modes. I forgot this is only odd frequency. Okay, so let's get there. So first, let's understand why is there factor of 1 over t and 1 over v here. T is the time, and then v is the system size in space, okay? So for each, let's focus on one mode and some particular frequency and particular momentum. And contribution of those modes is suppressed by 1 over time and 1 over the system volume. The reason is that each mode describes a macroscopic collective fluctuation, right? For example, k equals 0 mode is the mode where every rotor is fluctuating in the same manner across the whole system. And then certain frequency mode, m equal 1 mode is this mode, right? You start from 0 and then you do a half oscillation. So therefore, everyone fluctuates together. But the action itself is a sum of space and time, right? So therefore, the action for that mode will be naturally proportional to the volume of the space and time, because you have a integration and sum over space and time, right? So therefore, actual amplitude of each mode is small in the limit that space-time is large. Okay? Is it clear? That's why contribution of individual mode is small. It goes down. It goes to 0 when space-time volume is large. Of course, larger the system size, more modes there is. So this B actually runs from there are each, because there are L independent side, so L to the D independent side. You should have L to the D independent modes, right? So you have a finite number of independent modes in space, right? And then in the limit that L become large, the number of modes also become large. So therefore, basically here you are collecting small contribution from many, many modes. Okay? That's this factor of 1 over TV. And then this factor of G square is easy. In the weak coupling limit, when G square is small, fluctuation is small, so therefore suppression is small. Okay? So that is this factor. And then let's look at this. This is important factor. There is an inverse of this factor, omega square and E square, E. And that just reflects the fact that certain modes are easier to excite because it costs less action. And those modes that are easier to excite are the one where this factor is small, right? This is like almost acts like a mass, if you are willing to view that way. But the point is that the modes with a small frequency and small wave vectors are the one that cost less action for creating some unit amplitude fluctuation. Therefore, they will have larger fluctuation, right? Larger fluctuation means it creates more disorientation of this phase, more fluctuation in this phase, right? So therefore, it will contribute more in the suppression of the expectation value. Okay? So it is this is that factor. Okay. Any question about this point? Okay. Now, let's actually look at what happens, what is this first for the finite system. When system size is finite, the allowed momentum is discrete, right? So this sum over K is discrete, okay? But for the ground state, we still need to take the large T limit to completely project out all the excited state, right? And as we take the large T limit, the frequency, the interval between discrete frequency goes to 0, right? And in particular, by the way, here there are only other frequency modes that contribute for the reason that I explained. The even frequency mode do not contribute to the expectation value because it's a node at the position where we insert the operator. Okay, so there's only odd frequency. And then the difference between two odd frequency mode here goes as 2 pi over 2t, right? That's the delta W between two nearest odd integer m, right? And in the limit that t become very, very large, the step size omega become small, and then the smallest value of omega also become small, it goes to 0, right? And then this factor here, say 1 over 2t sum over omega, can be converted into integration because this thing, 1 over 2t is same as delta omega over 2 pi, right? And in the large t limit, delta omega becomes small, so therefore this is integration, right? So this sum over frequency become integration over frequency from 0 to infinite. It's from 0 to infinite because the frequency modes here are positive due to this boundary condition. So in this case, this expression can be written as, I still have, say, sum over k, so I have dv, and sum over k. But then I have the integration over frequency of this expression. Okay. And this integration is, I forgot the prefactor, but it is proportional to square root of 1 over square root of E of k. The prefactor is in the lecture note. Okay, I mean, this is something that you can exactly. So now that tells us what is the contribution of each k mode is to the suppression of the expectation value. And see here, okay, so let me ask, what is this? What do you think this number is? If you sum over all k here. So let me write explicitly here. Yeah, this is the expression. And this is the important expression to remember. Okay.
So if you blow to
this factor become infinite due to the k equals 0 mode. You sum over all k value, but for k non-zero value, well, this is still non-zero, right? So 1 over some big but non-zero value still gives some finite number. But when k is 0, this is strictly infinite because E of k is strictly 0. Okay? So it's a e to the minus infinite. So it's 0 for any finite volume. So this statement doesn't depend on dimension. In any dimension, as far as your system size is finite, the expectation value of that is 0 in the ground state.
On the k equals 0 mode is the classical mode?
So k equals 0 mode, again, is the mode where all the rotors fluctuate together without k describes the wave vector in the spatial oscillation of this fluctuating mode. Okay? So k equals 0 mode that they fluctuate together like this. Okay? And that is the most dangerous mode because that doesn't cost any energy. Right? Because energy depends only on the relative angle. So therefore, when everyone decided to fluctuate together, you can fluctuate without any energetic penalty, right?
So it will have an infinite weight on the action. This path has an infinite weight.
That's right. So that means this k equals 0 mode is wildly fluctuating to the extent that even if you start your seed state with some particular angle phi, these rotors manage to collectively fluctuate back and forth to explore all directions with an equal weight. That's why it becomes 0. Okay? So therefore, the conclusion is in any finite system, there is no spontaneous symmetry breaking in the ground state. They manage to find all possible direction due to quantum fluctuation. Here, there's no thermal fluctuation. This is purely quantum mechanical effect. Okay? Even if you prepare your initial state where all rotors are pointing in one direction, you allow them fluctuate due to quantum effect, and they manage to explore all direction. That's the conclusion. Okay. Now, something interesting happens when V is not finite. Okay. So let's first do the math and then try to understand that consequence. So when V is strictly infinite, right? Then what we have to do is you have an infinite system from the beginning. And then you prepare some seed state for that infinite system, right? And then you apply this cooling operator for some time t, and then make the t bigger and bigger to more and more project out the excited state, right? So in the V goes to infinite limit, the right limit to take is to first take the V goes to infinite limit first, okay? And then large T limit. Yes?
Yeah, so when you're very like infinite, it could be like an element with like periodic boundary conditions, or even it's really like totally infinite.
Here, boundary condition is not important. Yeah, I mean, you could have open boundary condition. As long as you don't break the symmetry, as long as you're Hamiltonian, commute with the total angular momentum, this conclusion still holds. But calculation is just easier with periodic boundary condition. Okay, so in the thermodynamic limit, what we have to do, this expectation value is given by the same expression but importantly, you have to take the large V limit first before we take large T limit. This is very crucial. In other words, you first have the infinite system size, right? And then you cool it. Okay, are you with me? Yeah. Then the first thing that happens is that, so again, when V is very, very large, the spacing between different discrete momentum also goes to 0, with the momentum spacing in each direction is 2 pi over L. Okay? And here, this factor of V is L to the D, right? And then this L to the D, 1 over L to the D, or sum over all momentum. And L to D is nothing but the delta K to the D over 2 pi over D over sum of all momentum. And again, this can be turned into integration over momentum. Okay? But when you turn this kind of expression into integration, you have to be careful about at the point where the integrand blows up. Right? So in principle, at k equals 0, it can be dangerous if the integrand is infinite, right? However, what protects that divergence is this omega. Because we are taking first large V limit at finite t. At finite t, omega is strictly above 0 because the allowed frequency omega there, lowest frequency is 1 over t, pi over t, right? So for any finite t, this omega is non-zero. Therefore, I can safely turn this sum into integration. Otherwise, if this was not there, at k equals 0 mode, this is infinite, right? So you cannot turn that infinite into this continuous integration. This is a little mathematical subtlety, but in order to rigorously kind of demonstrate the existence of spontaneous symmetry breaking, this is a crucial point mathematically. So then, this frequency integration is also turned into the frequency sum is also turned into the frequency integration. And at the end of the day, what you have is this. Again, I did a frequency integration using the same way. Mathematically speaking, only thing that I did in addition to this is turn this sum into integration. But here the subtlety is that in order to be able to do that, you need non-zero omega. Okay? So that is where I used the fact that I first take the large V limit before I take the small t, or large t limit. Maybe I have factor of 2 here. Oh, sorry. 8 here. Okay. So this is the answer you get in the thermodynamic limit when V is strictly infinite. Okay? And let's compute what this is. Where what really matters is this integration. First of all, the momentum is bounded. Its magnitude is bounded. Maximum magnitude is pi. Because we are looking at the discrete lattice, so the rotor cannot oscillate faster than momentum pi in space. Right? That's the largest possible momentum. So momentum is bounded from above. So therefore, this integration cannot diverge from large momentum because it's bounded integration. But it can still diverge if this integrand has singularity in the momentum space. And that happens near k equals 0, right? Because at k equals 0, epsilon k goes to 0 as k squared. So let's focus on this expression near k equals 0. So by replacing epsilon k with k squared, I'm correct up to some finite correction. Yes?
Yeah, when you wrote the integral, we saw the problem with this pole. Why did we make the integral on the frequencies before we take the integral on the momentum space?
Wait, the integral itself commute. You can do integration in any order. You get the same answer.
So, okay, if you can compute the integrals, why was it important to take the limit of V to infinity first?
For V is finite, you cannot write this sum over k into integration. So to be able to convert the sum into integration, this fact is important. But once you have done that, once you can do that, the integration of frequency and momentum itself commutes. So you can do any order you want. And this is just k, modulus k, right? So interestingly, the integrand itself diverges as we expected because k equals 0 mode is the mode with a zero energy cost. Therefore, its contribution is very large. However, depending on the space dimension, the result of integration may or may not diverge. So let's do it. So let's consider first d equals 0. That's the zero-dimensional trivial case, only one rotor, right? But let's do it anyway. In that case, this integration is just d k 1 over
There's no integral. If d equals 0?
Oh, d equals 0. Sorry. Yeah. Sorry, I meant d equals 1. Sorry. So in d equals 1, dk 1 over k, right? So that's the d equals 1. So it's a chain. Oh, well, d equals 0, we already know it's a finite system. So we already know there's no spontaneous symmetry breaking. So let's do d equals 1. And then, so largest momentum is pi. Its magnitude is pi, right? From minus pi to pi. So this is modulus. So it's 2 times of from 0 to pi, right? And then this is log, right? Of upper cutoff is pi, but the lower cutoff is 0. Okay? that makes this integration diverge. Even in the thermodynamic limit, in d equal 1, okay, in one dimension, this still diverges. So therefore, I forgot this e to the phi. Therefore, this expectation value still vanishes in d equal 1. Okay? So therefore, in one dimension, even in the thermodynamic limit, there's no spontaneous symmetry breaking. However, how about in d greater than 1? In that case, where I have, say, 2 or 3 dimensional integration here, right? And then you have, you can use the polar coordinate, and you do the angular integration first, and then radial integration boils down to dk, k to the d minus 1. This is the measure of the radial integration times 1 over k. So there's a d over 2, right? And for d greater than 1, this is finite. This is convergent integration. Okay? So this is finite. Right? For example, for d equal 2, this is just constant. D equal 3 is linear. But because of the upper cutoff, it's just some finite number. So therefore, in dimension greater than 2, expectation value of this operator is non-zero. In particular, it does depend on the angle of the seed state. So therefore, ground state does remember the directional information of your seed state. Okay, so this shows that in dimension greater than 1, space dimension greater than 1, the U1 symmetry can be spontaneously broken in the ground state. Ground state, there are infinitely many ground states because depending on what seed state you choose, you get different ground state. Otherwise, you wouldn't get different value of expectation value. Right? So there exists spontaneous symmetry breaking of U1 symmetry in dimension greater than, space dimension greater than 1 in the ground state.
The theta operator is Hermitian, right?
Hmm?
The theta operator is Hermitian.
It's not Hermitian. So maybe you are worried that this is not observer, but you can make Hermitian by adding e to the minus I theta. You get this?
No, I know, but only the theta.
Hmm?
Only the theta operator is Hermitian.
Yeah, so theta is Hermitian. E to the I theta is not Hermitian.
It's unitary.
Yeah, you can say it's a unitary.
It has to have eigenvalues with modulus 1, right?
But we are looking at the expectation value. Expectation value doesn't have to have modulus 1 because your ground state can have a component with a different direction. Yeah. So physically, what happens is that in finite dimension, although there's a strong energetic motivation for everyone to align along the same direction, we are subject to, in each of you, so imagine each of you are rotor, and then you are strongly coupled with your neighbor. But as far as the system size is finite, and you are subject to some quantum fluctuation, as you fluctuate once in a while, as you fluctuate right and left, once in a while, there's a moment where everyone turns a little bit left. There's a non-zero chance for the system to do that under quantum fluctuation, right? So that once in a while, everyone kind of change the direction a little bit, and if you wait long enough, then you end up exploring all possible directions. Okay? And that remains to be true in d equal 1. Although the system size is infinite, you have only few neighbors. Okay? So therefore, as you fluctuate a little bit right and left, you have only 2 neighbors. It's a very cartoon picture. And then as you fluctuate, your neighbor says, oh, that you're aligned in the wrong direction. But when you don't have that many neighbors, you can influence your neighbor instead of you being influenced by neighbor and go back to the original position. So it is possible that as you fluctuate, your neighbor also fluctuate along your same direction, and that can propagate across a system. So somehow system can find a way to explore all possible direction. That's what happens in D equal 1. But that becomes harder in higher dimension because you have more neighbors, right? In 2D, you have a neighbor from left, right, and up and down, right? So then you are more strongly influenced by your neighbor, right? So it's harder to convince 4 neighbors as you fluctuate. So therefore, once you start from seed state with a particular direction, you are basically stuck. Although in principle you can fluctuate in the limit that the system size is infinite, it's impossible for all of you to collectively find the right path to or fluctuate in the same way. Okay, that's why spontaneous symmetry breaking can occur in dimension greater than 1. Okay. Yes.
Can you repeat the argument for the integral, the d minus 2?
D minus 2?
Yeah.
Here?
Yeah.
Ah, okay. So you can just do this integration is 1 over d minus 1, k to the d minus 1, where upper cutoff is pi and lower cutoff is 0, right?
Yeah, that's fine. But we have 1 over modulus k.
Yeah, and then, then this one is, say, dk, k to the d minus 1 times angular integration. Well, in 2D, I'm just using polar coordinate. In 2D, when d equal 2, it's a dk, k, d theta, right? That's the measure for 2-dimensional integration in polar coordinate. And 3D, you have a d2 here, k to d2. Okay? Are you convinced now this spontaneous symmetry breaking can occur in the d greater than 1? Yes.
So you're saying that both system could have some waves propagating. So you said that in one dimension there could be some you pass some information to the other side, and then the other side pass to you. So you can propagate a wave.
Yeah, I mean, well, wave can propagate in any dimension, but in d equal 1, you are more vulnerable to quantum fluctuation because you have fewer neighbor, right?
So the velocity of this wave would be just omega over k?
Yeah, I mean, here in this unit, all velocity is 1 in any dimension. Yeah, because at low momentum, this is k squared. So actually, at low energy, you have Lorentzian, emergent Lorentzian symmetry, but that's not the main subject.
Real physical system, V is finite, right?
Yes.
But can you observe?
That's right. Okay, so that's a very good question. In any realistic system, V is finite. So that in the strict sense, in strict mathematical sense, there's no spontaneous symmetry breaking. And that's why your hard drive has only finite lifetime. Because in your hard drive, you are recording your information, a bit of information, in a piece of little magnet that can point in certain direction. So if it is pointing this direction, that's 1. If it is pointing that direction, it's 0. And this is big enough that, of course, here we have to consider thermal fluctuation as well, but it's big enough that it takes very long for this system to explore all possible direction. But the point is that time scale is finite, but still reasonably long. Maybe 10 years, so that we can use our hard drive for 10 years. But the point is that lifetime, the tunneling time is finite. By tunneling time, I mean time it takes for your system to explore from one angle to another angle. But as the system size become bigger and bigger, tunneling time become longer and longer. But it is finite in any finite system size. But if tunneling time become longer than our lifetime, to us it looks as if symmetry is spontaneously broken. But if you wait long enough, eventually your magnet or hard drive will tunnel into different direction, erasing the memory.
What effects we can observe with the spontaneous symmetry breaking?
Sorry?
What effects we can observe with the spontaneous symmetry breaking?
What if we cannot observe? Sorry, I didn't.
What effects?
What effects do we observe as a consequence of spontaneous symmetry breaking? Okay, that's a good question. Well, most manifest effect that you see all the rotors pointing in one direction, and they are stuck. Another important consequence is that you have infinitely many degenerate ground state, which also means that above the ground state, you can create excitation with arbitrarily small energy. And when that happens, we say the system is gapless, because you can create a mode with very, very small energy. So, and the modes, the gapless mode that arises in this spontaneous symmetry broken state is called Goldstone mode. I don't know whether you've heard about it, but it's just named. That just modes, the modes that where the direction fluctuate kind of globally, and that doesn't cost much energy. So therefore, that exists as an excitation, excitation that doesn't cost energy.
So, but we can detect these effects in microscopic properties that the magnetic field.
Yeah, yeah. This is the reason why you can have magnet that stick to your fridge. Yeah, yeah.
Well, last question. What systems we can describe with the dimension greater? Because
Dimension
greater than 3.
greater than
3.
30.
4 if it's
3 or 3.
Yeah. So what is the meaning? Because we can describe like the volume is not described by volume space.
Yeah, of course. Physically, only relevant dimension is 0, 1, 2, and 3.
We cannot we get another system that has more dimensions?
Oh, okay, good. Yeah, of course. Artificially, you may be able to create some link so that you can create, say, hypercubic geometry. That maybe, and actually that's interesting. And there are experimentalists whose atoms are sitting in 3 dimensions, but they kind of engineer long-range interaction such that this atom is coupled to that atom, such that as if they are close to each other. Okay, and effectively that system behave as if it's in four space dimension. So that can be possible. Yeah, and there are people doing that. Yeah, yeah. So if in principle, if you want to, I mean, higher dimensional theory is not in that sense purely academic subject in that sense.
So the principle behind the finite and infinite, the difference between the finite and infinite systems, is very similar to how the Graham canonical ensemble partition function is technically always analytic for finite systems, right?
Mm-hmm. Yeah, that's right. That's right. So that's right. So in any finite system, strictly speaking, there's no different phases of matter. They are all equivalent in some sense.
Something else that struck me as similar is this final analysis of when the transition occurs is very similar to how Bose-Einstein condensation is analyzed for different dimensions.
Exactly, yeah.
So D equals 1 doesn't happen.
Yeah.
D equals 2.
Yeah, this is exactly the same physics. Yeah, yeah. Bose-Einstein condensation also breaks the U1 symmetry spontaneously. It has the same phenomena. That's right.
is the correspondent to the straight line.
Yes.
So if we had chosen a seed state where we have rotators in different directions,
Initially?
yes,
Yes.
that wouldn't be true.
You mean how are there more than one saddle point path? Is that the question for some generic initial condition?
Yeah, because then we would have like different initial directions.
Yes.
And the rotators would have to fluctuate to, in the end, be in the same direction.
Yeah, answer is yes. In general, there are more than one saddle point solution. Actually, even in this case, this is not the only saddle point solution. More precisely, saddle point solution is defined to be the path around which action is locally minimum. This is the actually global minimum, but there are other local minimum. For example, if you have a winding, then that's another saddle point. Around one winding, small fluctuation around the winding always increase the action, so therefore it's a local minimum, but that's not the global minimum. So yes, there are multiple saddle points. So in general, to be more complete, you have to sum over different saddle point, and around the saddle point, you have to add the effect of the fluctuation. But here I have chosen the global minimum because the other contribution doesn't change the conclusion.
If we are, let's say, in this state where there are these fluctuations, is there any kind of effect where they tend to go again to this ground state that they like trying to synchronize again and try to move all together again?
Oh, okay. So, okay, interesting question. So you are saying initially you prepare your seed state to point in some random direction.
Yeah, and they are in these fluctuations and excited. Do they tend, because it has been seen experimentally.
That's right. Yeah, it happens. It happens. Yeah. So even if G is small enough, and if dimension is greater than 1, then even if your seed state doesn't have that perfect arrangement initially, ground state spontaneously organizes itself to have pointing in one direction. But in general, the ground state you obtained may be a linear superposition of ground state where all rotors are pointing this direction, and all rotors are pointing in this direction. It can be, in general, linear superposition of those macroscopic quantum states. So that can happen. Yeah. So those kind of states are sometimes called Schrödinger cat state. It's a macroscopically many degrees freedoms are in the same state, and they are the total state is kind of linear superposition of those macroscopic quantum states. Okay, so I have only 15 minutes, but this is good. I mean, the next topic that I wanted to discuss is the following. In D equal 1, we say that there's no spontaneous symmetry breaking because these rotors manage to explore all possible directions. But still, that doesn't mean the ground state forget everything about your seed state. It forget about the directional information, but direction is only one particular information about your seed state. Yeah? And your state may have a different information and does have different information, and some of the information might be retained in the ground state. Okay? In particular, one can have some kind of global property of your state. Okay, so this angle phi is more local property. Okay, because it determines the direction of individual rotor. Okay, so in the spontaneous symmetry broken state, if you just look at the one of the rotor, you know what happens across the whole system because everyone is pointing the same direction. So you can tell the property of the ground state just from the local property. But there are certain properties that are not locally encoded, but it's more globally encoded, so that you have to look at the whole system to learn about those properties. And among those properties, there are so-called topological properties. So topological properties are the ones that are globally defined for each state, and that doesn't change under small deformation of your state. Okay, so this will become more clear when I'll give you an example. So in 1D, for example, let's consider the case where G is small, so that nearby rotors are almost pointing in the same direction, but they explore all possible directions. So they don't pick particular direction. That means if you just look at the small part of the system, the relative angle is not that big. They are almost pointing the same direction, right? So, and then in the ground state, some of the bases may have this kind of pattern where everyone is more or less pointing where. Okay, let's do more. It can fluctuate very much from the beginning, but eventually like this. And also, you can have a different configuration where these fluctuate and wind around in some way like this. And then, if you look at only a few rotors here and here, and you don't see much difference. They are almost pointing in the similar direction, right? You cannot really tell the difference. But if you look at the whole thing, imagine there's a periodic boundary condition, so it's a ring. Can you see the difference between these two pictures? What is the difference? So here, these rotors fluctuate spatially, rotate, so it rotates counterclockwise a little bit, and then it rotates back and then comes back, right? So therefore, in the space of angle, if I say the first rotor was here, second rotor is there, and third rotor is there, and then you can have some trajectory here, right? Then in the first case, it deviates and then body come back like this, right? But in the second picture, it's different. You start from somewhere, and then, you start from here, sorry. And then as you move to the right, this rotor goes to here and goes to there, and then it goes around, right? So in the second picture, these rotors wind around the phase space once, whereas here it doesn't wind. And this is something topological in the sense that if you change the state a little bit, you change this state to this and this, okay? This winding number doesn't change. The fact that this doesn't wind doesn't change, right? Here too, you change the state a little bit, the fact that it winds once doesn't change. It's due to the fact that winding, how many times it winds around is defined as an integer. So integer cannot change continuously. And these kind of property are called topological invariance. So in 1D, we can define so-called winding number as follows. 1 over 2 pi, sum over all sides, and then like this. This square bracket represents the following. When I measure the angle difference between side I and I plus 1, okay? I insist that the difference in angle is defined in domain between minus pi and pi. Okay? Otherwise, if you don't have this, if you just sum them up, you have a theta 1 minus theta 2 plus theta 2 minus theta 3, theta 3 minus theta 4. So they all cancel, right? So there you don't see anything. But suppose I insist that when I measure the relative angle between two neighboring rotors, I insist that I measure this angle within, this is defined between, say, minus pi and pi. then this is well-defined, right? For any configuration of rotor, I have a unique number, right? Then in this case, as this rotor changes a little bit, when I have, say, theta 1 here and theta 2, this is delta theta, not this one, okay? That's my convention. Then as this rotor winds around, it adds up, always adds up, right? So that in the second case, winding number will be, it rotates, I guess, in the counterclockwise, it's a -1. Here, there is no winding, so the winding number is 0. In principle, you can view this as an operator. It's well defined. You can compute the expectation value of this in the path integration. Okay? But anyway, and then now, you can classify your state in terms of this winding number. You can, and then you have a state, collection of state like this with winding number 1. And there's a collection of state with winding number -1 and 1 and any integer. So there's any state belongs to one of these class. Okay? And we say these states differ from each other topologically. They are in different topological sector. That's a word, but it really means they have different topological invariant. And then the question is this. Suppose I choose my seed state from one of these sectors. Suppose I choose my seed state to be this state, winding number 0, one of the state, right? And we know that in D equal 1, symmetry is not spontaneously broken. So therefore, even if so for simplicity, let's choose this to be my seed state. This is kind of simplest winding number 0 state, right? All rotors are pointing in one direction. Okay? We know from our analysis, in the ground state, the directional information is lost. Right? These rotors explore all possible direction. The question is this. Does the ground state remember this topological invariant or not? Okay? That's the question. Or will ground state be able to tunnel from one sector to another sector and so on? If it can tunnel, then ground state will be given by linear superposition of states of all possible winding number. In that case, your ground state doesn't remember about this topological invariance, right? Or that's one possibility. Or ground state may remember topological number, even if it forget about the directional information. Even if it fluctuates from here to here, and all down like that, right? They can explore all possible direction. They may fluctuate within one winding number sector. That's another possibility, right? Is this question clear? Okay. And it turns out that in 1D, although there's no spontaneous symmetry breaking, depending on the value of G or T, you can have a phase transition. When T is large enough, okay, or G is small enough, the ground state remembers the winding number of the seed state. In other words, when G is small, if you start from this seed state, the quantum fluctuation fails to tunnel state from here to another sector. Okay? When it happens, we say there is a topological order. It just means that it doesn't fluctuate randomly. There's some order. There's some pattern in the fluctuation, in quantum fluctuation. And the nature of that order is topological. Okay? It's not local thing. When there's a spontaneous symmetry breaking, we say there's a local order. Again, in that case, it's not fluctuating randomly, right? There's some collective pattern. But that order is something that you can prove locally. For that reason, we call that there's a local order when there is a spontaneous symmetry breaking. But there's a local order when the tunneling from one symmetry sector to another sector is suppressed, when tunneling from one angle to another angle. And these two states are related by symmetry generator, right? Remember, angular momentum is the conserved quantity here. And angular momentum is the generator of the angular translation, right? So therefore, different states in the symmetry broken states are related by symmetry. That's what you will hear, okay? And then this order is related to the symmetry there. It's a local order. Whereas here, it's a global, and it's a topological. So I think my time is up. So
to use a few more minutes, I mean, we have lots of questions.
Yeah.
So to be able to be on one of these topological states to the other, there is a need for a phase transition?
Yes, there is a phase transition. As you tune value of t in 1D, when t is large, ground state is given by not only sum of all states with a different direction, but with a different winding number. That's what happens when t is small, when quantum fluctuation is very large. When t is large, fluctuation is still managed to average over all directions so that there is no symmetry breaking. However, the state is stuck in one topological sector. So there is a sharp phase transition. And that phase transition is called BKT transition, Berezinski-Kosterlitz-Dawlitz transition. Okay. And the nature of that is the topological phase transition. Okay.
Are these transitions related to some kind of long-range entanglement?
That's right. Yeah. I mean, by nature, topological order is long range because you have to know this topological only after you look at everything. So almost by definition, there is long range entanglement in the ground state. So let me just take 2 or 3 minutes just to sketch the existence of such phase transition. Okay. So, I mean, the details are in the note, so you can try to follow the calculation, but here's the picture. So this is my ground state. Now you have seen this so many times, so you can. And then suppose I prepare my seed state to be So then let's consider, say, a state with a winding number -1, say. Then it will be like this. Okay. So I want to know what is the tunneling probability, amplitude, from this seed state to this component in my ground state? If this is 0, that means there's no tunneling, right? If this is non-zero, then there is a tunneling, and therefore ground state will mix between different winding number. So mathematical question is, what is this? What is the path that connect this zero winding state into the state with the non-zero winding? Okay, and because winding number is different here, it's impossible to connect these two under smooth deformation. Somewhere in the middle, there must be some abrupt change to change the winding number. You can imagine it, right? And such path in this space-time is called instanton. That's just a name, but pictorially, the instanton looks like this. There's some point where there's some abrupt change, and around it, there's actually vortex like this. So vortex is something around which the angle of the rotor changes by 2 pi here, and that is what is needed to connect different winding number sector. And you can fill this gap, I guess. Yeah, okay. So I don't know, the nice picture is in the lecture note. Okay, but basically, there's a winding of the phase of the rotor around this point in space, at a localized point in space and time. Okay, there must be a vortex, because if I look at this as a whole system, right, and if I walk around the boundary of this whole system, say this way, walk around this boundary, along this path, the direction doesn't change, right? And at far infinity, say direction doesn't change. But along this path, the phase winds by 2 pi, right? And along this path doesn't change. So therefore, across this point, phase of the rotor has to change by 2 pi. So somewhere in the middle, there must be some center of the vortex, right? If you see some rotating flow, right, there must be a singular point. It's impossible not to have singular point. Okay, of course, here we are talking about the lattice system, so the singular point can be in between lattice. But so it doesn't cost infinite amount of energy because of the lattice. And then you can compute what is how much action is cost to create this kind of instanton, okay? And the calculation is in the note. The one way to do it is you choose the center of the vortex to be the origin of your coordinate, and then you can introduce some polar coordinate to compute the action for this instanton. And then instanton configuration is just theta as a function of r and phi. Here, r and phi is just the polar coordinate that I introduce around the center of the vortex, okay? And my rotor at this position in space-time is just phi in this case. Because as phi increases from 0 to 2 pi, theta also increases 0 to pi, right? So as we walk around by 2 pi in space and time, the angle of the rotor changes by 2 pi. That is vortex, okay? And then you can compute the action for this configuration, where you have a 2 derivative term in time, and there's some discrete gradient term in space, but at long distance scale, this thing, theta I minus theta I plus 1 square, can be viewed as a space derivative. Okay, and in addition to the time derivative term in action, your action can be written as 1 over g square space-time integration of this term. Okay, I'm just sketching. Okay, and then using this action, you can compute the action for one instanton. Has anyone done this kind of calculation? Okay, but for this configuration, the gradient, what is the gradient in the polar coordinate in 2D? It depends on your angle. So it's r derivative of this with r direction, then 1 over r, then the phi derivative of this in the phi direction, right? This is the gradient. And this is 0, and this is 1, right? So therefore, gradient is just 1 over r. So this is 1 over r squared. And I have two-dimensional integration over space and time. So I have 1 over g squared drr. This is, again, measured from polar coordinate, and I have 1 over r squared. Okay? And then if my system size is L, well, this is logarithmic, again, the same log. It's a log. And lower cutoff here is 1, because I have lattice spacing 1. So r cannot be smaller than 1. Upper cutoff here is the system size L. So the action for one instanton is logarithmically divergent in the limit the system size is very large. So instanton is a very expensive excitation in that regard.
Shouldn't the instanton be more probable on a bigger?
That's right. So where does it come from? Creating one instanton is very unlikely in the large system size because it causes so much action. However, and in the large system size, you can create instanton here or there, anywhere, right? So you have many ways to create instanton. And then in the full path integration, you have to sum over all possible positions of instanton, right? So although the probability for having one instanton at particular location is this small, okay? The ways that you can create instanton also scales with L, right? Bigger the system size, the more position you have, right? It goes as a L squared roughly, if this is both L. And then this quantity, I can write this as a e to the 2 minus 1 over g squared log L. And depending on the value of g, this quantity may diverge or not. If in the weak coupling limit, when 1 over g squared is large, right? Then this is negative, right? So therefore, even though there are a lot of ways to create instanton, cost of creating one instanton is so big. So the system doesn't want to have instanton in the path. So in that case, instanton is suppressed. So therefore, when g is bigger than certain critical value in this schematic is 1 over 2, instanton is suppressed. So therefore, ground state is stuck in one topological sector. Therefore, there exists a topological order. On the other hand, if g is become bigger, say bigger than 1 over 2 here, then this becomes positive, right? Then the contribution from this volume dominate. Although one instanton is very expensive, there are so many ways to create them. So overall, there's a very large chance to have instanton. Okay, that means there's a lot of tunneling between different topological sectors. In that case, information about topological invariant is lost in the ground state. And we say there's no topological order. So therefore, there must be a phase transition around the value where this vanishes. Yeah. Did you have a question?
Can we relate different instantons with others?
Yeah, so in general, you have to include a path where there are multiple instantons, right? Yeah, and then there are more systematic ways of including all those contributions. And you may, if you are interested, you can learn it from, you can study it through so-called renormalization group method. But well, here's the basic picture.
How can we observe vortices or instantons, or what are the applications of them? Because I went to a quantum computation seminar and I heard the word vortex a lot.
Yeah, I mean, okay, so vortex is usually used.
To repeat the question.
Yeah, so question is, how do we observe the vortex? Or what?
Yes, and the applications.
How do we use them? Okay, so this is vortex, but usually vortex is vortex described when you have a phase winding in space. Okay, for example, in the 2D rotor, if I have a two-dimensional lattice, then the rotor may have a phase winding around some point like this. Right? So this describes spatial texture of the rotor. Okay? This is vortex. And this is something you can observe. Okay? Here, it looks like vortex, but it actually describes space-time history. This is one-dimensional space. This is the imaginary time. It just describes one path along which this winding number jump. Okay. So, and how do we see this effect? Where this is the one that is responsible for tunneling. For example, one consequence of this is that when G is large, when this tunneling happens a lot, then you will have a unique ground state, because ground state doesn't remember about any information about your seed state. So there's a unique ground state, and then there's a non-zero energy gap above the ground state. And this gap is non-zero because of this tunneling events.
So, is the calculation of just one expected value an expectation value with seed space we imposed by hand and unsets sufficient to conclude that in the large T limit, the ground state doesn't remember the seed space, the seed state?
So you are asking question about spontaneous symmetry breaking?
No, because we just calculated one expectation value, right?
For this.
Yes,
Yeah.
and from that we concluded that in the large D limit, the ground state doesn't remember the seed state, right?
Doesn't remember about the direction of the seed
okay.
state. It doesn't mean it forget everything. Indeed, it doesn't forget everything, right?
Okay.
In D equal 1, it forget about the directional information. It forget about the phi. But it still remember the winding number.
So if we for example, computed another expectation value in terms of the angular position, we would conclude the same, right?
Yeah, so that's a very good question. So more generally, how do we know that my ground state, how do we detect collective behavior of my ground state, right? For example, before these people discovered this transition, people thought that in one dimension, ground state has no memory at all about the seed state, okay? And then they noted that actually some information about the global property is retained. So therefore, there could be other properties that the ground state can remember. Different topological property. So that's one of the kind of research topic. How do we classify different emergent phenomena? What are the observable that we can use to tell the difference, this ground state from that ground state? Okay? Many years ago, people thought local order is enough. If you just look at the local rotor, and if it is frozen in one direction or not, people thought that is enough. But now it's no longer true because of this topological information is also important. Even if this local directional information is lost, ground state can contain this kind of topological information. But we don't have a complete set of classification per se.
Okay.
Right. So that's a very important question and hot research topic.
Nice, nice. And another quick question is that I remember that in the last class you mentioned something about the scale invariance and the fractal behavior of such system. But now we have concluded that in infinite dimension, there's the U1 symmetry is broken.
Yeah.
So how do we keep the fractal behavior and
Okay,
still break the symmetry?
so let's say we are in D equal 2 or 3, okay? And there we know this U1 symmetry can be spontaneously broken. And then as you tune T over U, the nature of ground state change qualitatively. So when T is small, there's a unique ground state. And we also saw that there's a non-zero gap between ground state and the first excited state. We checked it only perturbatively in the small T limit, but that continues to be true. And then we also know that in the large T limit from the computation we did today, symmetry can be spontaneously broken here. Spontaneous broken symmetry. Okay? And then there must be some phase transition, okay, between these two limits. Okay? And then what happens at this critical point is that, say, if you approach this critical, and this is called quantum critical point, because this is all driven by quantum fluctuation. This is zero temperature. You're not tuning temperature, but you are tuning some parameters in your Hamiltonian. Okay? And then probably you remember that somewhere in this what we call insulating state, ground state is more or less the state where all angular momentum is zero, but once in a while you can have a particle-antiparticle pair created. And then in the deep insulating phase, the size of this particle-antiparticle pair is small. You know, if you remember in the space-time path integration, we have the sum over all trajectory of the particle-Hall pair. And the typical size of those particle-Hall pair is small. But as you make T bigger or U smaller, it is easier and easier to create those particle pair excitation, and the size of those particle pair increases. And then at this critical point, the size diverges. And then in your space-time path integration, you will have to sum over all particle pair trajectory with all possible sizes. So your ground state is given by some linear superposition of some sub of particle pair with all infinite sizes. So at that point, there's no scale. Of course, there's a lattice scale, but there's no scale associated with the distance between this particle and antiparticle pairs. And then if you are zooming out and look at your ground state at longer and longer distance, eventually you don't see anything about the lattice. Lattice spacing appears to go to zero. So, but you have no matter how many times you zoom out, you still have some large particle antiparticle pairs in your ground state. So therefore, you have a scale invariance. So therefore, this critical point is described by some theory that is scale invariant. And the name for those theories are conformal field theory. So this is a place where such scale invariant theory emerge. And then in general, it's very hard to understand quantitatively the behavior of conformal field theory, especially in D equal 2. It is still unsolved problem. Yeah. So that's where, say, fractal structure emerge. Fractal structure is just, even if you zoom out, you change the scale, it looks same. Yeah. Because scale is infinite.
Given that we are really out of time, I suggest that you ask the questions to Sung-Sik informally during the break, so that we can still start on time. So let's start in 20 minutes with the last dark matter lecture, and let's thank Sung-Sik for a beautiful set of lectures. But of course, feel free to continue to ask questions.